Welcome to the Theta Oilfield Services Rod Pumping Optimization video podcast. This is John Svinos.
This is John Svinos, and I would like to talk to you about designing Group 2 wells with RODSTAR-V or RODSTAR-D. First of all, I want to discuss what Group 2 wells are. Some time ago, I discovered that there are two groups of wells. Group 1 wells, which are the most common, have pump depths that are greater than 4,000 feet, and they can have any plunger size, or they can be less than 4,000 foot in depth with a plunger that is smaller or equal to 2 inches. And these groups of wells, are much easier to deal with when you're doing a diagnostic analysis, because the pump dynamometer card shapes for these wells only depend on the condition of the pump. So if you have a full pump, you're going to have a rectangular shape, for example, regardless of anything else that's going on in the system, regardless of how deep the well is, regardless of whether you're using steel rods or fiberglass rods. If the pump is full, you're going to see a rectangular shape. So it makes it easier to diagnose these types of wells. Now, Group 2 wells are different. They are less than 4,000 foot in depth, and they have plungers that are greater than 2 inches, like 2 1/4 or above. But of course, there is another factor involved, and that's the compressibility of the fluid. And the more incompressible the fluid is, the worse these fluid inertia effects are. So what that means is that Group 2 wells are much more difficult to diagnose because the pump dynamometer card shape is dynamic. It depends on pump condition, pump depth, tubing size, plunger size, fluid compressibility, and pumping speed. So a full card, it will never be a rectangular shape for these wells, and as a matter of fact, it'll vary in shape depending on one of these conditions. You know, how deep the well is, how big the pump is, how fast you're pumping. The downhole pump car shape will change. So that's why we need different tools for optimizing Group 1 wells versus Group 2 wells. For example, for Group 1 wells, you don't really need a predictive program like RODSTAR to find out what's going on downhole. You can simply calculate the downhole card or use XDiag, which does the interpretation for you. It's an expert system, and it'll tell you what the condition of the pump is. However, when you're dealing with Group 2 wells, especially if you don't have XDiag, then you need to have a predictive program that can handle or it can simulate Group 2 wells like RODSTAR. And both RODSTAR-D and V have this capability. Now, if you have XDiag also knows about Group 2 wells, and it can actually use RODSTAR inside to do a very enhanced analysis when it comes to these types of wells to tell you what's going on. But basically, what happens is, the basic wave equation can calculate the downhole dynamometer card, but when you look at that card for Group 2 wells, the shape is not that easy to interpret. Okay, so here we see an outline of the whole rod pumping system. In a Group 1 well, the rod stretch is the primary mechanism for absorbing the shock of picking up the fluid load. So because Group 1 wells are deeper and they have a smaller pump size, when they start moving on the upstroke, the first thing that happens is the rod stretch. That absorbs most of the shock of picking up the fluid loads. The plunger will actually not move until the rod stretch first. Another secondary mechanism, which is by far secondary, is fluid compressibility. In other words, if you have some free gas in your fluid that you're pumping, it's going to be compressible, so when the plunger starts to move up, it'll compress that fluid somewhat, which helps absorb the shock of picking up the fluid load. So in Group 1 wells, we have this situation. as you can see here, when we started on the upstroke, the stretch of the rods is very significant, so the plunger doesn't actually start to move when the polish rod moves on the upstroke until we have moved far enough on the upstroke to stretch the rods enough to pick up the fluid load with the plunger. But in group 2 wells, because the wells are shallow, the rods don't stretch much. So when we start on the upstroke, in this animation that's coming up here, there is no stretch, any significant stretch at all. So as soon as you start the upstroke, the plunger has to move up almost at the same time, or a fraction of a second after the polish rod moves. And what that does is it creates a pressure wave in the fluid as the plunger moves up, and also puts a large shock loading, which is a reaction of this plunger having to pick up the fluid and accelerate it on the upstroke. You see a large hump on the surface card and the downhole card since they're very close to each other. So this is what we call fluid inertia effects, and that is what makes group 2 wells different than group 1 wells. So instead of getting a rectangular looking downhole dynamometer card like you would expect for a full pump, instead you might get a card like this. And again, the reason for that is because as the plunger moves up, it puts a pressure wave into the fluid. That pressure wave increases the load on the plunger. You know, the fluid has inertia, and the plunger has to pick it up and accelerate it, so it's going to incur additional load on the upstroke, which shows up as a hump here at point B. Now, you know, this is a dynamic effect. So, and this pressure wave that we put in the fluid will move up at the speed of sound in the liquid that we're pumping. If it's mostly water, it's going to be about 5,000 feet per second, which is about a third slower than the speed of sound in steel. So what we will see is that as the plunger starts to move up, you know, it creates a pressure wave, which is indicated here with this red bar. So when it starts to on the upstroke, it creates that pressure wave, which can then move up, reach the surface, gets reflected back down, and if the well is not too deep, we're going to see a reflection of that original pressure wave on the upstroke as a smaller hump, because obviously as that pressure wave returns, some of it gets decayed, some of it you know, the energy gets absorbed in friction, and when it returns to the plunger, it's smaller than the original. But sometimes we definitely see some significant reflections that then make the load go up later on the upstroke. So as you can see, this card shape here does not look like a rectangle, and that's very typical for group 2 wells. Okay, so the conclusion is, because of the dependence of the downhole dynamometer card shape on fluid inertia effects in group 2 wells, any kind of library that you have for shapes, how to interpret downhole pump car shapes, that only works for group 1 wells. It doesn't really work for group 2 wells very well. All right, now let's get into the software. First, let's start with XDiag. Let's say that we load a case that it's a group 2 well in XDiag. Let's take a look at that. So this is the dynamometer card that we recorded for this case. We brought it into XDiag along with the data for the well. Okay, all the data is here. You can see the plunger size is 2 1/4. The depth of the well here is 2,170 feet. Actually, let me check that. That was the fluid level. It's actually 2,174. Okay. It has a Lufkin conventional 320, 298, 100 with 50 horsepower motor. So we're going to go ahead and run it and see what XDiag says about this well. That should always be your first step. You want to find out what the condition of the well is first, especially if you're optimizing an existing system, before you decide what needs to be changed or what needs to be redesigned to fix problems. It's always better to run XDiag than RODSTAR, because when you run XDiag, since you're measuring the dynamometer card, you actually find out what is really going on in the well now. Not, if you only use RODSTAR, then you're assuming that everything is in good shape downhole, but that may not be the case. Okay, so here it says the pump is full and it's in good mechanical condition. Excessive rod tubing friction was detected. The downhole card shows fluid inertia effects, which are normal for the well conditions you specified. The gearbox is not overloaded, but the unit is out of balance. The rostering is okay. And it looks like the load cell is off a bit, which the program automatically fixed. And also the calculated pump displacement is higher than the production, which may indicate that there might be a tubing leak. Now if you take a look at the dynamometer card, this is the surface dynamometer card, this is the downhole card, and as you can see, it looks like a leaking traveling valve, but because this is a group 2 well, that may not be what's going on. Actually the program says that it's a full card, so it's actually normal to have this shape. Okay, so that's the first step, and then we save this XDiag file, and then we can go into RODSTAR. So let's load the XDiag file that we just looked at into RODSTAR-V. The way we do that is we select open file, and then for file type here we drop this down, we go to XDiag files, and then we double click on the file we want to bring in. The program says that the XDiag fixed the load shift. We want to bring in the corrected card. We're going to say yes to that, and now the program brought in all the data for the well. Notice that the pump efficiency here is 75%, but you have to be careful. This efficiency is strictly a calculation from the entered production divided by the capacity of the pump. Now, this efficiency could be low, not because the pump is worn. It could be because there is a tubing leak, and actually in this case there is a possibility that there is a tubing leak here, as we saw in XDiag. So to get a good match in these types of wells, you need to have the right pump efficiency. That's one of the variables that affects what kind of a simulation you get for these types of wells. The higher the pump efficiency is, the higher the loads will be. Another variable that is different here, that you normally don't have to worry about in group 1 wells, is if fluid inertia is the fluid compressibility index. You see, when you include fluid inertia effects, and the program will automatically include those when it sees that the conditions that you have make this into a group 2 well, it will automatically include fluid inertia effects. Now, sometimes you actually may not need to include fluid inertia effects if there is no indication whatsoever that there are fluid inertia effects. Because in some borderline cases, you may not really have any detectable group 2 fluid inertia effects to worry about. So in that case, you don't really need to include them, but the program will include them by default. Also, the program will automatically pull in a compressibility index. In this case, it pulled that in from XDiag, but if there was no XDiag file, if you don't have an XDiag file and you are starting from scratch to design a new system, the program defaults to a compressibility of 3. And by the way, there is extensive help built into the program about group 2 wells and fluid inertia. So if you're in this field and you press F1, the program will explain what fluid inertia effects are in detail. So this might be a good thing for those of you that have group 2 wells to read, so you can better understand how group 2 wells behave and what you need to be putting in here. So what I wanted to show you is if I just go ahead and run the program without making any changes, what would I get? Well, first of all, I'm going to get a warning that says that a pump efficiency of 90 to 95% is recommended for shallow high rate wells, in other words group 2 wells, to ensure that the peak polish rod load, peak torque, etc. are not under predicted, which verifies what I just said before. The pump efficiency actually acts like a double variable in these types of wells. Not only does it affect the production that you will get, that the program will calculate, but also it affects the loads. So the higher your pump efficiency is for group 2 wells, the higher the loads will be on the upstroke. But the program says that you can use smaller pump efficiencies if you're trying to match an existing well. But obviously if you're designing a new system, you should be using 90 to 95% because you want to design it for worst case. And when you use 90 to 95% efficiency, the loads predicted by RODSTAR will be the highest. So that's why the program is saying that. You see, in my case, I didn't change the pump efficiency, which was brought in from XDiag. So if I say yes to continue using my data, what kind of a match would I get between my measured card and my predicted card? Let's take a look. Okay, I'm going to look at my dynamometer plot here. See, it's not bad, but you can see that the predicted loads, which is the blue line, are lower on the upstroke than the measured. So that's probably because the pump itself is more efficient than what this number calculates to be. Because part of that efficiency loss is because of the possibility of a tubing leak, not necessarily because the pump itself is not in good shape. So, you can have a 95% efficient pump, but if you have a tubing leak, that production that the pump is putting through is not making it to the surface. So let me try 90% efficiency here and see if I get a better match with the surface card. Okay. Well, it looks like it might be a little too high. So I'm gonna back down a little bit to maybe 85% efficiency. Also, the compressibility of the fluid makes a difference. So I'm not going to play with this compressibility index. And the other variable that makes a difference is the friction coefficient. So if I uncheck this, I see that the program is using 105 on the upstroke, 105 on the downstroke. Many times in these types of wells, you might want to increase the upstroke value and decrease the downstroke value, because usually there is more friction on the upstroke, because that's when you're pushing that fluid through the tubing. So there is more friction between rods and tubing at that point. So for example, I might want to make this like 1.5 instead of 1, and maybe instead of 1 I'm going to make it 0.5. Let's see if that gives me better results. I'm going to get that warning. Not okay. And let's take a look if we're getting a better match. Okay, it looks like I'm getting a better match on the downstroke here. Let me change my compressibility index. This might be a little too high. By the way, this variable goes between 1 and 7. 1 means it's highly incompressible. So like if you have 100% water, you would put 1. And 7 means you have some gas in your fluid and it's fairly compressible. So in this case, I'm going to select, let's say, a 3, which is basically the default. See what that does. So this takes some trial and error runs to get everything to check out and get a good match. Okay, so the shape is not bad, but it looks like my loads are too high, so I'm gonna lower my pump efficiency a little bit. I'm gonna go to 80% here. I'm gonna make another run. You know, the different variables that you change affect the dynamometer card in different ways. The pump efficiency makes the overall top of the card go up or down. I'm getting a pretty good match here. The compressibility affects the shape of the card. So it looks like here my compressibility is not correct because I'm not getting a perfect match. I mean, it's not bad, but I'm not getting a perfect match between the predicted and the actual cards. So maybe my compressibility is actually a little bit higher. You know, you can try up or down from where you are to see which one gives you a better match. So the compressibility, in other words, affects the shape differently than efficiency. You can see here that shape-wise, I got a little bit closer here, but not here. Let me go back to efficiency and put in like 70, 75% here. See what happens. Okay, so this is pretty good. As you can see, I put in 3.5 for compressibility, and I changed my upstroke and downstroke frictions, and I put in a pump efficiency of 75, and my results look like I have the best match. Now, you can spend a lot of time doing this, but it's really not necessary as long as you get, fairly close, like this. What I'm showing here, you pretty much have it. So this is the predicted card, the blue one, and this is the measured. And actually, if you look at the downhole card, it looks very similar to the one we saw in XDiag. So this is actually the shape for a full pump for this case. This shape is normal. Doesn't mean that the pump is worn out. It's the normal shape under these conditions because of the fluid inertia effects. So I'm getting a pretty good match here. Now, this is matching an existing case. But if you were to design a new case, for example, if I was designing this well from scratch, right? I want to design it for worst case. So in this case, what I would do is I would put my efficiency here to, between 90 and 95%. It depends what kind of pump you get and how close the fit is. But the higher this value is, the higher the predicted loads will be. So if you put 95%, you can get the most conservative answer you can get. And now, since I already figured out that this is the correct friction coefficients, I'm going to leave them as they are. And also, since I know, in this case, my compressibility here is 3.5, I would leave it like that. Now, in a new case, I probably wouldn't know exactly what that is. What is the correct number for this? In which case it would be a 3, but it's still not very far off from what we're going to get. And this is a single rod string, so that's fine. Otherwise, I would have the program design the rod string for me, and the pumping unit here, I'm going to check to see if that's going to work. The only other thing, of course, you have to make sure is that the fluid level that you put in matches the fluid level of the pump. So if here the pump depth is 2175, then you need to put a 2175 fluid level here to design for worst case. So that's what I'm going to do. Run it and see what my loads will be when the pump is full. Okay, and it looks like the only problem I see here is my rods are overloaded. But notice how the predicted card is quite a bit higher now than the measured. That's because the pump is 95% efficient here, which means the pump is in perfect condition, brand new. So it looks like I might have to change my rods from a C to a D. And that should take care of it. Let's make another run. Okay, so that took care of the problem with the rods being overloaded. Now they're 96% loaded. My gearbox is 80% for minimum torque and 90% for minimum energy, and everything else looks okay. So this would be a design that would work. Okay, so that's how this works in RODSTAR-V. All the features of RODSTAR-V are available. The only thing you have to make sure is, when you have group 2 wells, to include your compressibility, to include fluid inertia effects and with your compressibility index, and to put in the right pump efficiency, which is 90% or above. Because if you don't, you see, for example, if I didn't include fluid inertia effects here, first of all, the program would not be happy with me, and it would ask me, it would warn me that for the conditions that I specified, I may want to include fluid inertia effects. But if I insist, just to show you what would happen here, if I was to run this, okay, first of all, I'm getting a warning that my minimum load is negative, which means the pumping unit is coming down faster than the rods can fall. But let's see what the rest of the dyno looks like if I don't include fluid inertia effects. You see, the program uses a second wave equation to simulate the fluid inertia effects. And even though that doubles its execution time, that's the right thing to do for these types of wells. Otherwise, you will not get a good match. You will not get good results. As you can see here, the predicted card looks very different. Of course, it's going to look different from the measured because the predicted is with a higher fluid level and higher efficiency, but it doesn't look good. It doesn't look anywhere close to what I got with fluid inertia effects. Let's go back and include fluid inertia effects and make another run and see what we get. See how different that is from what we just got. See, take a look at that. The loads are much higher, much higher. The shape looks different, and this is the correct shape for this condition. So, this can affect your gearbox loading, your rod loading. So for these types of wells, you need to include fluid inertia effects to get the right results. The second wave equation kicks in, and it simulates the waves of that are created in the fluid when the plunger has to move up on the upstroke. So these are the fluid inertia effects. Okay, so now let's talk about how to do the same thing in RODSTAR-D. Let me close this program. And what I'm going to do here is, again, I'm going to start with the X diag. Let's say that we have a measured case for a well here. I'm going to pick a different well here. So let's say we have this well that we just analyzed. So let's take a look at the results of the analysis here. The pump is full in good mechanical condition. The fluid level is determined to be 925 feet from surface. The gearbox is 19% overloaded. The pumping unit is slightly out of balance. The losses is reading high by 554 pounds, and so forth. So and let's take a look at the dynamometer card. Here's the surface card. There is the downhole card, and it looks like the gearbox is overloaded. It looks like in this case the pumping unit is too small as compared to the requirements of the well. And also in X-Diag, we see the system design score is not very good. We're getting an F here because the gearbox is overloaded, the rods are overloaded, the pumping unit structure is overloaded. So, and also the minimum pulse load is negative. So it's like it has everything bad here. So whoever designed this well needs to come and and attend one of my classes here, or rod pumping optimization. So here are the numbers: gearbox loading, rod loading. Now keep in mind that these numbers that you get on this page, as it says up here, this is the system design score for worst case conditions, for full pump and fluid level at the pump. So this is not the score for how the well is running right now, but it's under worst case conditions. So that's why, if you look at what the loading is now, yeah, the gearbox is overloaded, but it's not overloaded as much as we saw in the previous page. And also the rods here are not overloaded for the existing conditions, but they would be if the well is pumped off. Anyway, I'm going to save this, and then I'm going to go to RODSTAR-D. Okay, so I'm launching RODSTAR-D, and what I'm going to do is I'm going to do the same thing that I did with RODSTAR-V. I'm going to load the xdiag file that I just saved into RODSTAR-D, and I'm going to try to match the RODSTAR-D predicted card with the measured. Of course, I can only change the predicted card. I can't change the measured. So I'm going to select here Open File, and for the file type, I'm going to select xdiag file type. I'm going to find the file here that I just saved. It tells me that the xdiag corrected a load shift. Do I want to bring in the corrected card? Yes, I want to bring in the corrected card. Okay, and it's actually asking me if I want to use the deviation survey from a previous run of this well. The program is smart enough to know if the previous run of this well had a deviation survey, and it gives me the option to bring it in. Well, I'm going to say yes to save time. So now I should have all the data that I need to simulate this well. Now RODSTAR-D is a little bit different than RODSTAR-V in that its damping coefficients are not the same as RODSTAR-V, and also they're not the same as what you see in xdiag. These numbers are actually smaller than what we see in RODSTAR-V, but they have a similar effect. Notice here that the program includes fluid inertia effects by default. In this case, our plunger size is 3 3/4 inch, which makes this definitely a group 2 well, along with the depth, which is 2009 feet from surface. So this is definitely a group 2 well. So let's just run it the way I brought it in, with the default upstroke and downstroke frictions, and see what kind of a match we get. First of all, we're going to get the same warning that our pump efficiency should be between 90 and 95%. And of course, if this was a new well that we were designing, we would want to have a pump efficiency above 90%. But in this case, we are trying to match an existing well, so we are going to leave it as it is. That was the efficiency that was brought in from the xdiag run. That number, of course, depends on how accurate your production data is. If your production data is not accurate, the pump efficiency that is going to be calculated by xdiag will not be accurate. And to get a good match between the predicted and the actual cards, you need to have the right pump efficiency. That has to do with the integrity of the pump. Okay, so let's take a look here. Well, we're not quite getting the match. Well, it's not bad, but here especially there is a difference. If we look at the dynamometer card by itself, we can see that we're a little bit off here by a few thousand pounds. So it's a pretty significant shift. So okay, so we know that we're too high, so maybe our pump efficiency is too high, and also maybe our compressibility index is not high, is not correct. So the first thing I'm going to do is I'm going to go to the pump efficiency. Let me go back to xdiag for a second. Notice that xdiag was calculating a pump efficiency of 77%, 77.5, right? So if we assume that the production that we had entered in xdiag is correct, then that's the kind of pump efficiency we should be bringing in, we should be using. So if I go back to RODSTAR-D, I can put that in. Okay, that would be probably a better number to use than the default of 85%. So let me make a run, with using that number to see what I get. Okay, I'm going to say yes to this to continue. It looks like I'm getting closer, so that's a better number than what I was using before. But another thing that I'm going to change is the upstroke and downstroke damping coefficients. Typically for these types of wells, that are shallower than 4,000 feet, these friction coefficients sometimes have to be lowered. For example, I might try half that, both on the upstroke and downstroke. Actually, that's less than half. I mean, no, it is half because it's 0.1, so it's 0.05. So let me run it again. You know, the program takes longer to run, obviously, when you include fluid inertia effects, because it has to use those two wave equations together, the regular wave equation for the rods and also the second wave equation for the fluid in the tubing. Okay, so you see we're getting a pretty good match here, especially on the downstroke, but the upstroke is still a little bit off. So we need to look at our compressibility index. It looks like we don't have the right compressibility index, because that is what makes the biggest difference in the shape, how the hump of the car behaves and how the loads go down and go back up. So the program brought in 1.5 from XDiag, but in this case I think the compressibility might be a little bit higher here. So let me try 3, which is the default. If I was to run the program from scratch, it would default to 3. So let me see if that gets me a better match. Now, the reason why it's important to do this is you need to know what that compressibility index is to get better matches from the software. So, you know, each well is different, and if you get the right compressibility index for your well, then you know, you can use it in your predictive runs in the future to get better results. So here it looks like I still don't have the right compressibility, so I'm going to go back here and maybe go higher a little bit more. Maybe I'm going to go to, I don't know, let's say 5. See what that does. You know, these are tough wells to simulate because they're affected significantly by a number of variables, including pump efficiency, fluid level, friction coefficients, and so forth. So sometimes you have to play with them, you know, in the predictive software to get a good match. But it is worth the time because it helps you understand what's going on in your wells, and it helps you get better designs in the future. Okay, so it looks like we're getting closer here, but I might want to lower my pump efficiency a little bit too, because it looks like I'm still high here on the upstroke. So I'm going to go here, instead of 77%, what if I put in 70, let's say 70%? Is that going to give me a better match? I don't know. Let's take a look. Okay, again, we're getting closer. Okay, so I'm going to be changing also my compressibility index to 4 here. Let's make another run. Oh, and I'm going to I also changed my downstroke friction a little bit to 0.03. Let's go ahead and make another run. Okay, let's take a look at the results here. And we got pretty good match actually. Yep, take a look at that. That's pretty good. So anyway, you need to just play with these variables until you get the right combination of variables to give you the best match. So, you know, what we did here to get a good match is, let's take a look at that input. I used the pump efficiency of 76%, pretty close to what we saw in the program. Actually, I can probably go back to 77% and it's going to be fine. And the compression, you know, I use different upstroke and downstroke damping coefficients, 0.05 on the upstroke, 0.03 on the downstroke. I put in a compressibility index of 4. The rostering is the same. Yeah, nothing else is changed. So let's go ahead and run it again. So now we get a pretty good match. Now, what I didn't tell you is that this is not actually a deviated well, but a vertical well. And I wanted to discuss how you can take a vertical well and simulate it in RODSTAR-D, which actually allows you to simulate either a vertical well or a deviated well. As you can see, I'm getting a very good match here. So I'm going to go ahead and save that case. But what I was saying is that you can actually trick RODSTAR-D into simulating a vertical well by putting in a deviation survey like this. See, this well is 2009 feet deep. So I put in a deviation survey, just 4 points. You always have the first point here, at surface 0, 0, 0. But then I put in 3 other points, also with 0 inclination and azimuth. And that tricks the program into thinking this is a deviated well. Well, it is, I guess, but it doesn't have much deviation since everything is straight. But the program uses the algorithms that it normally uses for deviated wells to run this case. Now, I could have done this a different way. I could have switched from the vertical to the deviated, from the deviated to the vertical mode, and done it that way. But sometimes I prefer to use RODSTAR-D because it has more sophisticated calculations than RODSTAR-V, and even though it takes a little bit longer to run, the results might be a little bit better in some cases. So that's why I did that. So I tricked the program into using the deviated algorithms. Okay, so now that I got a good match and I have the right compressibility index for this well, which is 4, now what I want to check is what would happen under worst case conditions. So if my goal here is to pump the well off, right, then I want to design this system for a fluid level at the pump, which is 2009 feet. So I'm going to copy this, and then I'm going to go to the next window, and I'm going to put that for my fluid level. Okay, I'm going to leave my pumping speed as it is, and the reason for that is because I want to see what the pump capacity of the system will be under worst case conditions. In other words, how much production can the system make. But another thing I need to change is my pump efficiency. I'm going to use 95% efficiency because, again, remember that affects the loads for these types of wells, and you want to calculate a design with the highest loads to make sure that the rods or gearbox will not be overloaded, or the structure of the unit. So I know that if I leave the rods the way they are, the grade D rods, they're going to be overloaded. So I might as well switch now to a stronger rod, let's say a Norris 97 high strength rod. Now the pumping unit, I know the pumping unit is kind of maybe too small for this well, but I'll keep it for now. Let me make a run. Let's see what we get for production. My plan here is to use the production that the well calculates as my target production, and then I'm going to have the program recommend a unit size. So it looks like my motor size is not big enough. I need to go to 60 horsepower instead of not 50. So I'm going to do that. Okay, and as I suspected, my gearbox is way overloaded under worst case conditions. You can see that here. Let me zoom in here to the dynamometer card. You see the permissible load line, the red line, cuts deeply into the blue line, which is the predicted surface card. So the pumping unit is definitely way too small. And sometimes we see that because some people may have designed these wells without using a wave equation that can simulate fluid inertia effects. Those make a big difference. So what is our production here? That's why I made that run in the first place. So let's take a look at that. The production is about 1,500 barrels a day. So what I'm going to do So I'm going to go to the second input window here. Instead of putting in a pumping speed, I'm going to put in my target production of 1,500 barrels. Okay, and then I'll keep the same pump size. I think that that's okay. I'm going to keep the rostering the same, 1 inch. But for the pumping unit, now the program is recommending a 912, 253, 192. So if I click here to select that, the program will go to the closest unit available without the recommendation, which is this one right here. And this is actually a Lufkin Mark II, which may not be a good unit for this well because of the fast downstroke speed of the Mark II. So I'm not going to go to a conventional here instead of a Mark II. So I'm not going to swap this unit with a conventional. So let me go with a Lufkin conventional. The program is recommending a 912, 305, 144. It found this is the closest unit to that with crank hole number 2. So that's fine. I'm going to keep that. I'm going to ask the program to recommend the motor size for me. And now I'm going to run it and see what we come up with. So remember, when you're designing these types of wells, group 2 wells, you need to make sure when you're designing a new system to put a high pump efficiency, 90 to 95%. I recommend 95% because that will give you the highest loads. If you have an existing system that is close to, or that is the same or similar to the one you're designing, then do this overlay comparison that I did, between X-diag and rod-diag to get your compressibility index right. That way you get better results, and also the upstroke and downstroke friction coefficients, and that should help you get a good design. As you can see here, I'm not overloaded. My structural loading is 81%. My system efficiency is 47%. My gearbox loading is now 87%. So it's not overloaded. My rods are fine, 66%. So everything looks good. So with this kind of a design, I can get the production I need to pump the well off, but without overloading anything. Thanks for your attention.